Hello. I would like to thank the organizers for the opportunity to talk at this wonderful event. I will tell you about Ramanujan graphs, who actually started 40 years ago. So where does this story start? Where it began? So Budapest, June 86. So if you look at the date, we're really there. They probably got the preprint a week or two before because they don't open letters if you ever corresponded with them. So I guess that today they actually got the preprint. And the background was that at that time there was a large ongoing search for expanders, which are, as we all know, graphs with small adjacency eigenvalues, which is something we're going to hear a lot about. And this paper kind of settled a very big search. So this is the background for the paper, but the real more important background is that these were the 80s. And the world was cool back then. So where it really began is in California at the 80s with two mathematicians looking for a joint project to work on together. So as you know, photography did not exist yet back then, but with modern technology, we can get a pretty good idea of what they look like. And this is what they gave us. Ramanujan graphs. Okay, so from now on, that's it. Formulas.
You didn't do Phillips.
What?
You didn't do Ralph Phillips.
That's true, because I don't know him. I feel... Okay, so what is the Ramanujan graph? We're going to look at the k+1 regular graph, and it's called Ramanujan if the non-trivial adjacency eigenvalues are bounded by twice square root of k. And there are also the trivial eigenvalue, which are k+1 and minus k+1, which correspond to the constant functions and perhaps to bipartiteness of the graph. And this bound is optimal. This is what's called the Alon-Bopana theorem, which tells you that if you're looking at an infinite family of k+1 regular graph, and all of their non-trivial eigenvalues together, going to get at least to 2 times square root of k. So you cannot find an infinite family with smaller eigenvalues. And there is a conceptual reason for this bound, which is kind of, the tree is the optimal expander, right? You take a set in the tree, and you look at its neighbors, and it always grows. It always expands. So you cannot beat the tree, and the spectrum of the tree is this interval from minus 2 square root of k to 2 square root of k of Kesten. You need to work a bit to go from this conceptual reason to actual proof, and this is the Alon-Bopana theorem. And the question is, how do you construct graphs which actually achieve this bound, and what can you say about them? So here are the Lubotzky-Phillips-Sarnak graphs. You take P and Q, distinct primes, congruent to 1 mod 4, and you do this. It's actually a very simple construction. It's a Cayley graph of PGL2Q, which you construct as follows. You take I to be a square root of minus 1 modulo Q. You look at the integral solution to writing P as the sum of 4 squares. You take the ones where A0 is odd and the others are even, and you construct from them P+1 matrices in PGL2Q, and you look at the Cayley graph. That's it. It's a very small construction. It's very easy to describe. It's very, very hard to prove that these are actually Ramanujan graphs. It's not something that you can explain. It's something you have to build. You have to go through half of 20th century mathematics to understand why this is Ramanujan, in a sense. And so this is the construction, and the other question I asked is what can we say about them? And I'm going to talk about one property of Ramanujan graphs, which is the cutoff property. And this is a very nice example of something which is true for Ramanujan, and we don't know, at least, if it's true for expanders in general. Not like it does for Ramanujan graphs. So there's a paper of Eyal Lubotzky and Yuval Perez from 2016, which shows that Ramanujan graphs exhibit the cutoff phenomenon. So the Diaconis Shachshachani, Shalom Kostes, there are several people who discovered this phenomenon of abrupt mixing. So we look at a random walk or Markov chain, and we look at the L1 distance from the stationary distribution, stationary state, and the mixing occurred abruptly. So there's a short window where you go from not mixing at all to completely mixing. And this became very popular under the 7 shuffles are enough in the popular science. And to make it precise, let's look at the distribution. This is Percy Diaconis, by the way, also 80s, California. Remember? You could be a magician and a mathematician. And you look at the distribution of a random walk at time t. You have some vertex where you started from. And you ask about the epsilon mixing time, which is the first time at which your distance from uniform distribution is at most epsilon. And we take here the total variation distance, which is L1. Same thing as L1. And we want to have this for any starting point to be epsilon, at most epsilon away from uniform. We ask, when does this happen? The cutoff phenomenon is a phenomenon where this time doesn't depend on our epsilon. So we ask it about a family of graphs, like we do for expanders, and we say that this family has cutoff at a certain time with a certain window. If the size of the window is little o, smaller order of magnitude than the time, so think about this is the time of the cutoff and the window. The window should be small comparing to where it actually happened. And you go from 1 minus epsilon mixing, so not mixing at all, to epsilon mixing within this window, so between t minus w and t plus w. And it's a big conjecture that this phenomenon holds in much more generality than we know how to prove, but for Ramanujan graphs, we now know how to do that. So what do Lubotzky-Perez do? Rather than looking at the simple random walk, they first look at the non-backtracking random walk. The non-backtracking random walk, it just means that you cannot visit the last vertex you were at, and you can associate this with a Markov operator, which takes 2 vertices, so the one you're at now and the previous one, and you ask, where did I come from? Okay, I came from this one, and before that I was at another vertex, which is not where I am right now. So that's non-backtracking, but eventually it's just an operator on functions on edges, because 2 adjacent vertices where I'm now and where I was at the previous step, it's just a directed edge. So I can think about this as an operator acting on function on directed edges and look at the mixing of this Markov operator. And the big problem is that this is not a self-adjoint operator. Unlike adjacency, if I go from one edge to another one, I cannot go back. That's not how the non-backtracking walk works. This is what makes everything non-trivial. So, but to do the spectral analysis, it's actually something that was known very, very long ago. So there is the Ihara-Bas-Hashimoto zeta identity, which relates the adjacency matrix and the non-backtracking matrix. So A is adjacency, B is the non-backtracking. And this is a very nice identity, which we'll hear more about this week, which relates them. And you can translate this to actually translating between the eigenvalues. So given an eigenvalue of the adjacency, what it tells you about eigenvalues of the non-backtracking, and vice versa. And you work it out and you discover that this is the non-trivial spectrum.
Just passing, they are not the same size matrices, right?
Um,
And then like I
No.
just need to check that the polynomials are the same. That like
the polynomials, yeah. Yeah. The difference between the sizes of B and A is the Euler characteristic. This completes the degree.
What is K?
Our graphs are K plus 1 regular. So that K. Ask questions, please. So then I know that you're here.
What is Kx plus? What is Kx plus? It's a matrix, it's a number.
What?
X squared. What?
kx squared.
Put I here, yeah.
Oh.
Yeah. I actually thought, should I put it now? And I shouldn't. But essentially I could say just the statement about the spectrum. So the non-trivial spectrum of the adjacency matrix, to be Ramanujan, we want it to be contained in the spectrum of the adjacency operator on the tree, which is, as we said, the interval. That should be minus 2k, 2 squared k. And this is equivalent to the non-backtracking spectrum to be contained in the non-backtracking spectrum on the tree. And this is not real anymore. This is not a self-adjoint operator. This is a circle of radius square root of k and 2 extra points at plus minus 1. And this square root of k is the square root of the number of steps you can take, because the graph was k plus 1 regular, but now I'm in a non-backtracking random walk, so I only have k options at every step. And the spectrum is bounded by the square root of the degree. And this is really what stands behind cutoff. From this, it's kind of pretty easy to get cutoff.
Is that really plus minus 1 or plus minus k?
What?
Is that really plus minus 1?
Plus minus 1. Yeah.
Not plus minus k.
Yeah, because that's the tree.
Ah,
The tree doesn't have the trivial ones. Yeah. And what Lubotzky and Pell show is that the non-backtracking occurs because of this at time log kn. Now this is an optimal time because your walk is k regular. So to see, we have n vertices or n edges. To see all of them, you have to take at least log kn steps with a window which is order of log n. And that was a huge breakthrough. It kind of seemed optimal when they did it. They had good reason to assume that you cannot do better. And then Nestoridi and Sarnak showed that no, you can. And they showed that the LPS, the Lubotzky-Phillips-Sarnak graphs, actually achieve window which is O of 1, which is does not depend on the size of the graph. So we say this is bounded cutoff, which is very interesting, and I probably won't talk about it. And then from non-backtracking random walk, you can go back to simple random walk. You just think about simple random walk as non-backtracking random walk, where once in a while you take a step backward. And it just causes a time delay, and you get a cutoff at a later time. But the analysis is through the non-backtracking operator. So this is a beautiful property of Ramanujan graphs. And then we want to generalize things to other situations. So ask me about this later, if you want. And we want to ask, what is Ramanujan in other settings? So we can talk about non-regular graphs. We can talk about hypergraphs, simplicial complexes, directed graphs, manifolds. And the question, what can we say? What is this Ramanujan thing? And here is, I think, the first answer that was given. K plus 1 regular graphs is the same thing as quotients of the K plus 1 regular tree. And Greenberg, Yossi Greenberg in 95 showed in his PhD thesis that you take any tree and you take an infinite family of quotients of the tree, you take their non-trivial eigenvalues, eventually they have to accumulate to at least the spectral radius of the tree. And so here you have non-trivial, never mind. And he suggested, so let's call a graph Ramanujan if every eigenvalue is bounded by this spectral radius of adjacency operator of its universal covering tree, which is a good suggestion. And trivial eigenvalues here mean Perron-Frobenius eigenvalues. There's a whole theory which says what is the trivial eigenvalue for a finite graph. For regular, it's the degree. So this is one suggestion, and let's take a big example and see how things play out. So we're going to take the next simplest case, which is biregular but bipartite graphs. So almost regular, these are bipartite graphs, and each side has a constant degree. So the degree on the left is big K plus 1, on the right is little k plus 1, and they're different. These graphs are exactly the quotients of the biregular bipartite tree, which has alternating degrees at every step. And the spectrum of this tree was computed, and it's more interesting. Now it's not an interval, it's two intervals and a point. So it's a biregular graph, so the spectrum is always symmetric around 0. You have this strip here, which is of width 2 square root small k around square root large K. You have its minus, and you also have the point 0. This is the spectrum of the tree. So what should we call Ramanujan? We can say what Greenberg suggested, that we want the non-trivial spectrum of our graph to be bounded by the spectral radius of the tree, which is this value. Or we can say, no, we actually want all the eigenvalues to belong to the spectrum of the tree. So not allowing eigenvalues here between 0 and the strip. So do you have a feeling about this? What do you prefer? The first one? The second one? Okay, people like the second one. The question is neither. The answer is neither. We're going to ask for this. We want the spectrum of the adjacency operator to be contained in the spectrum of the tree, and we want the number of zeros in the spectrum to be correct. So this is a bipartite graph. The right side has to be larger than the left side because the left side has larger degree. And this means that the adjacency operator has to have a kernel on the right side, just because it goes to something smaller. So you have to have at least R minus L zeros in the spectrum, and we want to have this and no more. So no kernel on the left side. And maybe you wonder why. Okay, but before that, let's give them names. So we call the first one weakly Ramanujan, this one adjacency Ramanujan, and this one Ramanujan. Yes.
So like the extra R minus L pieces are like the trivial eigenvalues?
You could, no, not in the sense that we call trivial. They should be there. They belong to the tree. No, they're not trivial. They belong to the tree. And kind of the next one do not belong to the tree.
Just the multiplicity of 0, right?
Yeah, the multiplicity of 0. But why a certain number of zeros agree with the tree and more than that doesn't? That's the question. And here's one way to explain this. Really, this what we call Ramanujan is really equivalent to having the non-backtracking spectrum of the graph contained in the non-backtracking spectrum of the tree. So this is equivalent to this statement about the adjacency. So now you see already that being adjacency Ramanujan does not tell you that the spectrum of the non-backtracking is contained in the spectrum of non-backtracking on the tree. So you might have problems if you want to do analysis using non-backtracking operator.
So if you want to be finishing for an arbitrary graph, you take this. And
This one or
Yeah.
this? No, we have better one. Stronger. I'll say a word
Is
later.
it better or worse? The next one?
Yeah, depends what you want to prove or use. So what is the spectrum of non-backtracking on the tree? So we have again a circle, the circle of radius 4th root of kk, big K, small k. We have the point at plus minus 1, and we have two new points at I square root of little k, minus I square root of little k. That's the spectrum of the tree. And this radius, 4th root of kk, is really the square root of the Perron-Frobenius eigenvalue of the non-backtracking operator. So the Perron-Frobenius is the geometric, how do you call it? Square root of product? Mean, no, geometric mean, yeah. The geometric mean of the degrees of non-backtracking on right side and left side, so k times k square root. This is the Perron-Frobenius. And we have here the square root of the Perron-Frobenius, which is exactly what we want if we're trying to prove cutoff. And you could ask, what does adjacency Ramanujan translate to in terms of non-backtracking spectrum? And it turns out that if you're adjacency Ramanujan, so it means you have the correct spectrum but possibly too many zeros, then in the non-backtracking spectrum, you'll see that as 2 extra points at I plus minus I square root of big K, which is outside this circle. It sits here and here. So it's too big. It's not the square root of the Frobenius. Questions? Okay, so we have 3 definitions. Can we construct Ramanujan graphs, and what can we say about them? So I cannot not mention Marcus Spielmann-Srivastava, the beautiful paper from 2015, which among other things show that there exists infinite family of weakly Ramanujan bigraphs for every 2 degrees you choose. And so this is kind of an existence proof. It's not an explicit construction, but it shows that they exist. And it's also weakly Ramanujan. It's not adjacency Ramanujan. It's not really Ramanujan. You cannot improve the argument. Kind of we tried, they tried, and you cannot. It seems that you cannot get proper Ramanujan with this method. So let's look at LPS graph, Lubotzky-Phillips-Sarnak graph, and ask where did they come from? How did they get them? And the real answer is that it's not what we explained earlier with the Cayley graph. That's a red herring. What they really do is they take a p-adic group and look at its Brouwer-Titz tree and take quotients. So this is a p-adic Lie group. This is the projective unitary group associated with the quadratic extension of a p-adic field. Any p-adic Lie group acts on a nice discrete geometric construction due to Brouwer and Titz called the Brouwer-Titz tree or building. In this case, for this graph, the Brouwer-Titz tree is a p plus 1 regular tree. And we're going to, and they actually take certain quotients of this tree. Yes?
Set up in the construction geometry have to be 1 with 4. This means that adding I to Q.
1 with 4, so this is not a field. That's what's bothering you.
So, okay.
Yeah, that's fine. It's an étale algebra. And really, as Shaul pointed out, yeah, this is actually PGL2QP. It's kind of, you can actually write an isomorphism between them for any odd P. If P is 1 mod 4, it's easy. If P is 3 mod 4, it's a bit harder. But it's the same thing. So if you know the Brouwer-Titz tree of this group, it's the same group. But you're better off thinking about it as the unitary group. Why? Because the quotient you take is by unitary subgroups. So this is the LPS XPQ graph, and it's the quotient of the tree by this specific subgroup. So we take matrices, unitary matrices with entries in Z 1 over P, which satisfy a certain congruence condition, congruent to I mod 2Q. And this is where the Q comes from. And then there's this big machinery which translates the problem of studying eigenvalues and eigenvectors of the graph to language of representation theory of the p-adic group, and then translate it further to a language of automorphic representation of PU2 over the adels. The adels are the product of all the p-adic fields and real field, and this is where number theory kicks in, and you can use deep machinery, deep knowledge, and what underlies the fact that these are Ramanujan graph is the statement that all infinite dimensional automorphic representation of PU2A have tempered local factors. So tempered is what gives us Ramanujan eventually in this machinery. It's not due, but you can, it comes from the Lin and Jacquet-Langlands. So if you take both of these huge results in number theory, the Lin proof of the Ramanujan-Peterson conjecture and Jacquet-Langlands correspondence, then that is included in there. That. Yes? You can take, you can take U to be any number not divisible by 2 or P. Yeah, and that would work. Now, the fact that these graphs, that the LPS graphs are Cayley graphs, happens for a completely different reason. It happens because if you take lambda p1, so you take q to be 1, it means that you're actually looking only at matrices which are identity mod 2, and that's it. This group acts simply transitively on the tree. And this means that you can identify the tree with this group, and then you can identify quotients of the tree with quotients of this group. But now this is an arithmetic group, modulo a congruent subgroup, and Q, mod Q is exactly the kernel of the reduction mod Q. So what you get is your original group, lambda P1, reduced mod Q. And then you can show that it's actually PGLFQ or PSL. But this has nothing to do with why it's Ramanujan. And there is a third miracle kicking in, which is that it has logarithmic girth, which also does not come from any of the other reasons. So there are three miracles happening here. The logarithmic girth, for example, is used for proving the bounded cutoff by Margulis and Sarnak. So this is the LPS, and now we want to mimic that. So let's go to PU3, QP, and see what we get. So the good news is that if you take P to be 3 mod 4, and you look at PU3 of the quadratic extension QPI over QP, the Bruatis tree is a biregular tree, which is exactly what we wanted to study. So it's specific degrees, so PQ plus 1, P plus 1, biregular. So we would want to look at quotients of this tree by congruent subgroup of the P arithmetic subgroup of PU3 and hope that everything works fine. And it doesn't. So we can again translate everything to p-adic representations and then to automorphic representations. And then we discover that automorphic representation of PU3 can have non-tempered local factors. So these non-tempered local factors, for those who know the terms, are what's called endoscopic lifts of automorphic representation of smaller unitary groups. This is something that comes in the Langlands program. And this was first noted by HUJI and Piasecki-Shapiro already in '79 in a paper called Failure of the Generalized or Counterexample to the Generalized Ramanujan Conjecture, showing that automorphic representation beyond GL2, where the Lin shows that everything is tempered, do not have to be tempered. So yeah, you don't have to get Ramanujan graphs. And another question is, how do you describe the quotients? Because LPS is Cayley graphs, but Cayley graphs are always regular. So you need to do something else. So I'll tell you about a big project we've been working on for several years with Shai Evra, Brooke Feigun, Catherine Morishat, and myself. So let's take an example. So I'm switching from the Gauss field to the Eisenstein field. I'm looking now at QP extended with a third root of unity, right, rather than fourth one. But still everything works the same, so it's a quadratic extension, unitary group, it acts on a biregular tree, when P is 2 mod 3 now. And we take this. So this is kind of our analog of the LPS lattice. So associated with the P we began with and a new Q, we take all the P arithmetic matrices in the unitary group, which are congruent to I mod Q, and now we needed to find some weirder congruence condition at 3, which is the special prime here. And for this lattice, we can understand things. And it's not trivial, but the bottom line is take the quotient of the tree by these congruence subgroup. Let's call them XEPQ. E stands for Eisenstein. They are adjacent to Ramanujan, and they are not Ramanujan. So that is what we can show. So each of these are interesting because we show that they are not Ramanujan. It's not that we don't know whether they are. We can really show that they have bad
Never Ramanujan?
eigenvalues. What?
They are never Ramanujan?
Never.
Oh.
Yeah. Well, yeah, never. So here are examples. So the adjacency spectrum is real, so it's boring. So I'm drawing the non-backtracking spectrum because it's in the complex numbers. And you remember there was the tree. The tree had this circle and 4 points inside. And we said that adjacency Ramanujan, which is not Ramanujan, gives you 2 extra points on the imaginary axis outside the circle. So we always get them. That's how we first discovered this. We computed spectra and saw it appearing, and then we had to work really hard to prove that it continued to appear for every cube. So it's adjacency Ramanujan, it's not Ramanujan. But, why is it adjacency Ramanujan? We said that there are these endoscopic lifts, which are automorphic representation, which are not tempered locally. And we can show that is actually not the hardest. That is actually, no, sorry, that includes the laws that we didn't do. But you can show that it only contributes the plus minus I big square root of big K to the spectrum of the non-backtracking, which means 0 to the spectrum of the adjacency. This is why it is adjacency Ramanujan, even though we are not in VGL2 anymore. And we have other lattices which are fine, which are completely Ramanujan. So you remember that was E, here we have XG and XM. We constructed several families of lattices, and you see that these ones don't have the bad eigenvalue. So these are fully Ramanujan. So we can have both of them. And we have various criteria which tell you that no endoscopic lift occurs for a certain quotient, but we don't know. We have families that we still can decide whether they are Ramanujan or not.
When you say endoscopic lift, you mean any endoscopic lift or endoscopic lift from something trivial, a curve?
I can't hear you else. Yeah.
Your enemies are not just endoscopic lift, but those will be used to as a curve, right?
My enemies? I said,
If you endoscopic lift from U1 times something infinite dimensional, the U2 disappear.
Yeah.
yeah, yes,
Yeah, what we have.
yes, yeah. These are fine. Yeah. Yeah, there's a really specific one that appears here that we have to
So that's
fight.
what you mean by endoscopic of this.
Non-tempered endoscopic. That's the
Non-
one
yeah.
that we're fighting.
Yeah, true. How much time do I have? No, not too much. So I want. Okay. And then the other thing we wanted is to have an explicit description of our graph. So we came up with something we call Cayley bigraphs. And it's a bit more technical. So instead of giving the definition, I'll give an example. So take Q, which is 1 mod 3, omega, a cubic root of unity in FQ, and rho is a certain element. And we take 9 elements of the group. I didn't write, it's here, in PSL 3FQ. So these are 3 matrices, but J varies, so there are 9 elements in this set. This is a set of 9 elements in PSL 3FQ. And our graph is the following. It's bipartite. The left side is the group, PSL 3Q. The right side is composed of triplets of elements from the group, where you take an element from the group and multiply it by an element from this set and its powers. So the element, S square and S square. These are all elements of order 3. And the edges are just inclusion. So if an element belongs to a set, then you put an edge there. So this is these are exactly the graphs X2Q.
So is it possible to describe it as a branch covering?
A branch covering?
Yes.
What do you?
I mean, so the standard Cayley graph can be described as a covering. So
As a cover? Why is it covering?
There are no torsion in the curve. It's just that because it's a bipartite and non-regular, because of that it looks to you like
No, it means like.
I mean, like orbifolds and so.
Oh, yeah. You can do that, and sometimes you have to look at orbifolds. Yeah. Yes. To take into account the stabilizers. Yeah. Some of the computation we had earlier were actually like that, the spectra, and we had to work very hard to understand. Yeah. Then I understand what you're talking about. Yeah. It does occur. And I'll say that what underlies this this description is the fact that if you take our Eisenstein lattice and put 1 in Q, then you get this kind of full group acts simply transitively on the left side of the tree. So you cannot act transitively on the tree, you have different degrees, but we found a lattice that acts transitively on the left side, and then we use it to give a combinatorial description of quotients. That's the idea. So this is kind of here, this is our biregular LPS, and we can ask, okay, can we prove cutoff? But remember, these graphs are not Ramanujan. If they were fully Ramanujan, then kind of the Lubotzky-Phillips machinery works pretty nicely. But these are not Ramanujan, right? But still, we can prove that these graphs, as Q grows, have non-backtracking random walk cutoff at the critical time. So this is the this is the average degree, log of the average degree of n with a bounded window. So as small as you could hope. And why can we prove that if it's not Ramanujan? And we're looking at the non-backtracking random walk, so we really should be bothered by this bad eigenvalue outside these circles. And the answer is the density. So Sarnak's density philosophy, which is kind of a way to correct the failure of the Ramanujan conjecture. And the philosophy says that in the arithmetic world, in the arithmetic realm, violations of Ramanujan are not too many. And philosophy says that they should be sparse enough to be ignored. And to be ignored for question which kind of ask on average behavior, not worst case. In our case, let's say what it really says. So let's call this bad eigenvalue, the multiplicity of the bad eigenvalue, we call it EX. And so it's kind of either you can think of I square root big K in the spectrum of B, or the number of excessive zeros in the spectrum of A, we call it EX, and we ask how many of them are there. Sarnak Q density hypothesis, if you translate it to this setting, tells you that there should be roughly square root of the number of eigenvalues. There's a tilde here, which is up to polylog factors. But this is roughly square root of the eigenvalues. And we prove that is even better. Actually, the number of bad eigenvalues it's even O tilde to x to the 3/8. And from this is enough to prove cutoff. And remarkably, it's enough to prove cutoff with bounded window. So it's really, we got as good as we got from the Ramanujan. The size of the window may be grown, but it's still O1. So qualitatively, we didn't lose anything from the fact that Ramanujan fails in high dimension. And what happened here really is that you have a bad eigenvalue. So, there's spectral analysis. You cannot deny the existence of this eigenvalue. But the real point is that you care about a specific time. And at this critical time, this bad eigenvalues did not grow, is not dominant yet. So it's something very subtle. And we don't know whether all of this machinery is really needed. So what if we had adjacency Ramanujan bigraphs, which are not Ramanujan, and do not satisfy Sarnak Q? There are really too many bad eigenvalues. We don't know how to prove that they don't have cutoff. So everything is very open, but what we know how to do is use Ramanujan or density to prove things. And, okay, questions so far? Yeah.
You know the here?
Yes, yeah, it's logarithmic, and this goes here. We need it to prove bounded cutoff.
This condition of the x to the
You have to speak louder.
the condition of the x to the 3/8 gives you cutoff. Is this for this specific family or it's in general?
All of our families, but we do need the logarithmic cutoff, which you know how to prove for all of our families. And we need either Ramanujan or Sarnak Q. and a bit more with some transitivity. Okay, so let's go to higher dimensions. So we kind of covered graph. Okay, we didn't cover graph. We covered.
The simple anthropomorphic is.
Oh yeah, yeah. It's in a. You can compute the delay, and it's exactly where it's supposed to be.
The delay.
What?
What would be the delay depending on the short period, the large period, or both?
Yeah, you take this time, and you count the expected distance you get away from the origin at a step. So you need to compute what is the probability you get farther away and back, and the inverse of that is what you need to put before. That's it. So it's really like a time delay, because sometimes you go back. So we covered regular graph and biregular graph. And biregular, what I want to point out that was already very interesting. There are a lot of new phenomena. It's not like a copy-paste of everything that happened for regular. We encounter a lot of things. So go to 3 regular now, 4 regular. What can you say? So it's kind of very interesting. What can you say for graphs in general? But instead of that, we'll go to higher dimension. So let's replace graphs with simplicial complexes. And we're not the first to do that. So Ramanujan complexes is a term coined by Lubotzky-Phillips-Sarnak and Vishne. In 2005, Winnie Lee called it Ramanujan hypergraphs in 2004, and I think gave the same definition. Before that, there were other attempts, but these are really the two first one who kind of got it right. But the point is that once you look at higher dimension, there are many operators you can look at. Already in graphs we had adjacency and we had non-backtracking, but now you have simplicial Laplacians, you have geodesic flow operators, you have up-down walks, which people in computer science like working with. So what do you look at? And the answer is yes. So you look at all of them. So we define a geometric operator on X to be an operator that if you lift it to its universal cover, it commutes with the symmetries of the universal cover. This is something that adjacency does, non-backtracking does, and this is kind of the thing you need to do representation theory. So this is geometric operator, and we call Ramanujan complex a complex for which any geometric operator has its non-trivial spectrum contained in the spectrum of that operator lifted to the universal cover. Here, non-trivial spectrum is actually, okay, so what is trivial now? And that's not that simple, so we'll ignore it. But we know what we want the non-trivial eigenvalues to satisfy. They need to come from the universal cover. So this is, first of all, this is genuinely stronger than the Lee LSV definition. They only looked at the operators working on vertices. And we already saw that in biregular graph, which we have graphs which are Ramanujan with respect to vertices, but not Ramanujan with respect to edges. So this is really a stronger definition. This is what you asked earlier. So that's what we want in general. Yeah.
Collection of geometric operators. Does it have an algebraic structure? Is it
Oh, yeah.
algebra? Is it an algebra?
Yeah, we study it using Hecke algebras eventually. In the examples that we can understand.
Is it essentially somehow polynomials in the Laplacian?
That would be very nice. When it happens, we can say a lot. I mean, this definition is very, very general. In the setting that we actually work, yes. Okay, so let's take an example. We'll stick with PU3, but we'll take the other prime. So again, with U3 of the Gaussian numbers, but we took P which was 3 mod 4, and we got biregular graph. If we take P which is 1 modulo 4, then our p-adic group becomes isomorphic to PGL3, and then the corresponding Brouwer-Titz building is 2-dimensional. So the Brouwer-Titz building is an infinite, contractible, 2-dimensional complex that this group acts on. And the edges have a natural coloring because it's kind of 3-partite, and you ask whether this edge goes there or there to one of the other two parts. And there are Hecke operators, AI, still working on vertices. And AI is the adjacency operator, but only along edges of color 1 or of color 2. And this is the operator that were used to define Ramanujan complexes by Lee and Lubotzky-Samuels-Vishne. But we only have two of them, and they actually, how do you call it, adjoin to one another, so it's enough to look at A1. And in fact, okay, so let's look at A1. According to Lee and LSV, a quotient of the building is Ramanujan if the spectrum of A1 on the complex is contained in the spectrum of A1 on the building. The spectrum of A1 on the building is this. It's a kind of deformed triangle made by going over two real numbers on the circle and taking a specific symmetric polynomial in them. It's a nice area of the complex numbers. Because it's not the adjacency, it's not a self-adjoint, not the full adjacency, it's not self-adjoint, and you have complex spectrum. Interesting point is that this is actually equivalent to full Ramanujan for PU3. Like in regular graph, adjacency Ramanujan, forced non-backtracking Ramanujan, PU3 is kind of simple enough that A1 tells you everything. If you're Ramanujan with respect to A1, then you're Ramanujan with respect to any geometric operator in any dimension, in cells of any dimension. But this PU4 is already different. But we'll use that. And we'll use this to look at quotients of the building and ask whether they're Ramanujan. Now, something new which happens here is now there are infinitely many non-tempered representations which occur as endoscopic lifts, local factors of endoscopic lifts. So you remember in the bigraph, in the biregular tree, we had one bad representation which gave us this bad 0. And now there's a continuum of possible representations that can be local factors. And the picture you get is this. This is kind of what you want, the Ramanujan spectrum. And you have the eigenvalue which come from endoscopic, from non-tempered endoscopic lifts. And together they give you the automorphic Hamantash, which is comprised of the Ramanujan filling and the endoscopic crust. And these are several examples. So these, for example, come from the Eisenstein lattice, which we said does not satisfy Ramanujan. And you see that along the endoscopic crust you have eigenvalues in each quotient. And these quotients are of our Gauss lattice, and all the spectrum is within the filling. And you should think about it as poppy seed, which is the best filling. So this is how it looks in higher dimension. What?
Arguably.
How much time do I have? 10 minutes? Yeah. Okay. I think I'm pretty good. Okay. So these are, we can get either Ramanujan or non-Ramanujan. And let's talk a little bit about what is Sarnak-Shu in more general terms. So now take G to be a general semi-simple p-adic group. Let's say it's simple for simplicity, and we take a complex unitary irreducible representation. And we ask about the rate of decay of matrix coefficients. So to this representation, we associate sigma, which is the infimum of P, so that the representation has matrix coefficient in LP. And what we kept saying, tempered, just mean sigma equal 2. And then bad representation, non-tempered representation, endoscopic lifts have larger sigma. And the Sarnak-Shu density counts them. So let's take a co-compact lattice and look at L2 of the quotient and denote by L2 sigma of the quotient the subrepresentation with rate decay sigma. And you can states Sarnak-Shu density hypothesis, saying that for a compact subgroup K, now you remember that in general these representations are infinite dimensional, but if we look at the subspace of K fixed vector for a compact open subgroup, then it's finite dimensional. And we ask what is the K fixed part of the part with matrix decay, coefficient decay sigma. And Sarnak-Shu tells us that go over all sigma, alpha, and above, and it should be bounded by the total dimension to the 2 over alpha. And here we still have this O tilde, which allows extra logarithmic factors. Now, what happens if you take 2? If alpha equals 2, then we're asking about temporal representation. Here we get dimension to the 1, which is everything. So that's fine. We're saying, okay, we allow as many temporal representations as you want. But as alpha grows, you allow less and less. And you can ask, do you allow alpha to go to infinity? And we do not. So we also ask that there is some upper bound, some R, so that after this R, there are no matrix coefficients before infinity. There are actually also L infinity representation, which are the finite dimensional ones, which gives you the Perron-Frobenius eigenvalue at the end, but we don't want others. So this is Sarnak-Shu, and oh yeah, yeah, yeah. Well, that's a good question. Does it depend on K? That's actually a good question. Like if you had, that's a question, exactly the question of can it be non-tempered? Yeah. So if you have a non-tempered representation with maximal spherical, which is say Ivahori spherical, do you have also one which is maximal spherical? I don't know.
Oh wait, maybe one should stress. In high rank, R does not depend on K or on gamma.
Ah, you have a bound, yeah, that's true. You can give a bound which comes from the group.
Yeah.
But it could be that for specific K, something lower would work. I don't know. But we have, yeah, in our setting we have.
Also in rank 1 you have a bound.
What?
Also in rank 1 you have a bound.
In rank 1, for like Selberg,
Because you don't have almost invariance.
because we don't have
Almost invariance.
almost invariant. Yeah.
I mean, I think this is stronger. This is closer to property K. It's not how more. How more is not enough.
No, I don't think so. I think it's like property tau. So you have to have some Selberg, something, some spectral gap.
Yeah.
So this is Sarnak-Shu. So this is the general picture. And what we did in really recently, so this is something we did last week, finished a proof of a very general theorem. So in 3 minutes, I'll tell you what we can say now. So this is work with Rahul Dalal and with Shai. So take a simple p-adic group, take a cell in the Brutitz building, and take a sequence of geometric operator on the orbit of this cell. So this sequence can be, for example, the powers of the adjacency matrix or power of some Laplacian or geodesic flow. And it can also be not powers, it can be any sequence of operator. For example, going to all edges of distance L from you. That's not powers, but it's a nice sequence of operators. And if this sequence of operators satisfy 2 conditions, which the first one is almost exponential growth. We want the degree to be almost d to the L for some fixed d. So we allow to deviate by FL, where F is any monotone sub-exponential function. So you can modify, you can fluctuate with any sub-exponential function. And the second one is some kind of transience. We need the number of ways to get from a fixed cell to another fixed cell is globally bounded. You cannot return too many times, infinitely many times to one cell, or even more and more times to different cells. You have to have a global bound on the number of ways you can get from one point to another. And if we have these 2 conditions, and we take a family of principal congruence quotients of the building, which satisfy this hypothesis, the Sarnak-Hsu hypothesis. And now we'll make it precise. We'll say that the total dimension of subrepresentation with matrix decay at least alpha, well, we know it should be bounded by n to the 2 over alpha, but we also had this O tilde there. And now I want to make this tilde explicit. So I'm saying I'm allowing an extra log n to the k. So this is how many extra log factors I allow. And we have a bound on the total matrix coefficient decay before infinity. Then the sequence has cutoff. And it has the cutoff at the right time, which is log dn. And the window is going to be at least some constant time log n, where this constant is r times w plus dimension plus k plus 1. So what? So R is the total bound on the matrix coefficient decay. WG is the size of the spherical veil group of G. The dimension is the dimension of the building. K is the K that appear here in the O tilde of the Sarnak-Hsu. And 1 is the number 1. And I'm just saying, I mean, that's a constant. Why do we care about the constant? Because it kind of tells us that all these things go into the proof. It tells us that to actually prove this, you need to study the geometry of the building and the structure of the group and understand what happens there. And it's pretty interesting.
Oh yeah, I have a question about this. Like, when you say that a window is bigger, it is still in the scale of log n, but you need to pay this, like you also...
That depends on f. If your f is polynomial, then yes. If f is super polynomial, then you also have to have a bigger...
Okay, so somehow f, the upper bound on the window, f also gets in.
Yeah, but the interesting thing is, it's not written, but for any sub-exponential f you take, we can find w, which is a little o of log n. Yeah, that's cutoff. Yeah.
Just to make sure we're on the same page, so R is going to limit the worst thing that can...
Worst matrix decay, yeah.
And such an R does occur.
Oh, sorry?
And such an R does occur, like this
Yes.
is the lower bound.
Yeah, we can, yeah. For a specific G, it's like twice the rank or something like that. Yeah. So thank you very much, and happy birthday, Alex. So you would say take the covering tree, take its full automorphism group. We know it has to be a bit interesting if it has a finite quotient. Look for all the operators which commute with this automorphism group and ask for Ramanujan for each one of them. Now, we know that you don't always have for a specific, like there was a paper of Alex with Tatiana Naglibeda, it shows an explicit tree which has no Ramanujan quotient. You don't always have it. But this is kind of, the number theoretic, representation theoretic machinery is really strong. So it's like when it gives you Ramanujan, it gives you that. It really gives you for all geometric operators. So we ask for that, but it's true that if you want to construct graphs, maybe you don't need all of them and you can settle for less for whatever you're interested in.
Any more questions? Then let's thank Ori again.